starting chapter 3, which is titled Probability and Trigonometry, and section 311 is titled Using an Area Model. If you have your own calculator, that might come in handy today. If not, just watch how I use mine, and then you can use Desmos later. All right? We're going to be answering the question, how can I represent it? So for question 1, it says, it's in the genes. Can you bend your thumb backwards at the middle joint to make an angle? So you're going to hold up your thumb, see if you can bend it back, like the example at right. Or does your thumb remain straight? The ability to bend your thumb back is thought to rely on a single gene. What about your tongue? If you can roll your tongue into a U shape, you probably have a special gene that enables you to do this. Assume that half the U.S. population can bend their thumbs backwards and that half can roll their tongues. Also assume that these genes are independent. In other words, having one gene does not affect whether or not you have the other, and randomly distributed or spread out throughout the population. Then the sample space of these genetic traits can be organized in a table like the one below. So for part A, it says, according to this table, what is the probability that a randomly selected person from the U.S. has both special traits? That is, what is the chance that he or she can roll his or her tongue and bend his or her thumb back? Okay? So for bending thumbs, you have half yes, which means you have half no. For rolling the tongue, you have half yes, which means you have half no. But what are the chances that you're going to have yes, yes? So you take the 1/2 and you multiply it times 1/2, and you're going to get 1/4. Since all of them are 1/2 times 1/2, they're all going to be filled with 1/4. Okay? So the answer to part A is 1/4, which is equal to 25%. So if you have your calculator, here's how you get from 1/4 to 25%. You're going to take the 1, you're going to divide it by the denominator 4, you're going to hit the equals, and it's going to give you 0.25. To get 25%, you're going to leave that answer in there, hit times, notice it takes the previous answer, times 100, and that's how you get the 25%. Okay? For part B, it says, according to this table, what is the probability that the person has only one of the special traits, and justify your conclusion. So if you only can bend your thumb, you're 1/2. Or if you can only roll your tongue, you are 1/2 as well, which is 50% of the population. Okay? Part C does not really have a question. It says this table is useful because every cell in the table is equally likely. Therefore, each possible outcome, such as being able to bend your thumb but not roll your tongue, has a probability of 1/4. Part D. However, this table assumes that half the population can bend their thumbs backward, but in reality, only 1/4 of the U.S. population can bend their thumbs backward and 3/4 cannot. So if they ask us to rewrite it, 1/4 is yes, 3/4 is no. It also turns out that a lot more than half, about 7/10 of the population, can roll their tongues. How can this table be adjusted to represent these percentages? Discuss this with your team and be prepared to share your ideas with the class. Okay? So for rolling the tongue, we had 7/10. That means we have 3/10 that are no. So to fill in each of the boxes, we have to multiply top times the right. So 1/4 times 7/10 is 7/40. and 3/4 times 7/10 is 21 over 40. 1/4 times 3/10 is 3 over 40. And 3/4 times 3/10 is 9 over 40. Right? Anybody still writing? All right, turn over to page 2. What? Oh, okay. Good? Okay. So turn over to the top of page 2, and we're going to be talking about something called the probability area model. So for question number 3-2, it says one way to represent a sample space that has outcomes that are not equally likely is by using a probability area model. An area model uses a large square with an area of 1. The square is subdivided into smaller pieces to represent all possible outcomes in the sample space. The area of each outcome is the probability that the outcome will occur. For example, if 1/4 of the U.S. population can bend their thumbs back, then the column representing this ability should take only 1/4 of the square's width, as shown at right. Part A says, how can the diagram be altered to show that 7/10 of the U.S. can roll their tongues? Copy the diagram and create 2 rows to represent the probability. We just did this on page 1, so see page 1. Part B says, the areas of the regions represent the relative probabilities for different outcomes. For example, the portion of the probability area model representing people with both special traits is a rectangle with a width of 1/4 and a height of 7/10. What is the area of this rectangle? What does the area mean in terms of 2 traits? Okay? So we're going to take the 1/4 that's right here and the 7/10 that's right here and multiply them together. 1 times 7 is 7 and 4 times 10 is 40. So we're going to have 7 over 40. Then you're going to take your calculator, and on your calculator you're going to do the numerator divided by the denominator. So 7 divided by 40. That's going to give us the decimal of 0.175. Then we need to times or multiply by 100. That's going to give us a percentage of 17.5. Okay? Move that calculator down a little bit so you can see the steps that we did. Okay? Part C says, what is the probability that a randomly selected person can roll his or her tongue but not bend his or her thumb back? Show how you got this probability. So we're going to take the 7/10. We're going to multiply it by the 3/4. 7 times 3 is 21. 10 times 4 is 40. Punch 21 divided by 40 in the calculator. You're going to get this decimal. Then you're going to multiply by 100, and it's going to be 52.5%. Problem 3 says, 3-3, you and your best friend may not only look different, you may also have different types of blood. For instance, members of the American Navajo population can be classified into 2 groups. 73% of the Navajo population has type O blood, while 27% has type A blood. Blood types describe certain chemicals called antigens that are found in a person's blood. So part A says, suppose you select 2 Navajo individuals at random. What are the probabilities for type O and A for the 2 individuals? This time, drawing an area model that is exactly to scale would be challenging. A probability area model like the one above is still useful because it allows you even without drawing it to scale, complete the generic probability area model. So it says you're going to see the area model and you're going to fill it in right here. Okay? So to calculate this space, you're going to multiply 73% times 73%. 73 out of 100 looks like this on a calculator. Let me move it down. 0.73 times 0.73, which is going to get you 0.5329. So to get the percent, you multiply times 100, and you get 53.29. You do that for each of the boxes, okay? So for this box and this box, you're going to multiply 0.27 times 0.27. Then you have to multiply that by 100. I did that box. That gets you this box, the 0.27 times the 0.27. Now let's do this box, the 0.27 times the 0.73. Then multiply by 100. So it's 19.71. Okay? All right. Part B says, what is the probability that the two Navajo individuals selected at random have type A blood? So type A and type A would give you 7.29, which we're going to call roughly 7%. And then what is the probability that they have the same blood type? So if they have O and O, it's roughly 53.29, and if they have A and A, it's 7.29. Add those two together, it's 61%. Okay? Anybody still writing? All right, turn over to the top of page 3. At the top of page 3, we're going to do the problem called shipwrecked. It says Zach and Nick, both from Vermont, are shipwrecked on a desert island. Zach has been injured and is losing blood rapidly, and Nick is the only person around to give him a transfusion. Unlike the Navajo you learned of in problem 3.3, most populations can be classified into 4 blood types: O, A, B, or AB. In Vermont, approximately 45% of people have type O blood, so we put 45 right there. 40% have type A, so we put 40% right there. 11% have type B, so there's 11. And 4% have type AB, so there's the 4. While there are other ways in which people's bloods can differ, this problem only considers these 4 blood types. So in your group of 4, once we separate, you are going to make the probability area model representing the blood types in the problem. If you don't have your own personal calculator, you're going to use the Desmos scientific calculator. Okay? List Nick's possible blood types along the top, which is already done for you, and Zach's possible blood types along the side, which is already done for you. For part B, you're going to find the probability that Zach and Nick have the same blood types. So you're going to fill in all of these boxes using your calculator. Luckily, 2 people do not have to have the same blood type for the receiver of blood to survive a transfusion. Other combinations will also work, as shown in the diagram at right. Assuming that their blood is compatible in other ways, a donor with type O blood can donate to receivers with O, A, B, or AB, while a donor with type A blood can donate to receive A or B. A donor with type B can donate to a receiver with B or AB. But a donor with type AB can only donate to AB receivers.